We have already discussed some spontaneous cell reactions are utilized to produce this electrical energy in electrochemical cells. And also we have considered the electrochemical cells are reversible, means the EMF of these cells are determined by means of a potentiometer, which actually draws a very infinitesimal small amount of current to maintain the reversibility of this cell. And you all know the reversible thermodynamics could be applied only to these reversible cells. And by measuring the EMF, we can calculate the different properties of this cell, the cell reactions and some physical constants. Actually, what we shall do, the several physical properties and physical constants of these electrolytic solutions are connected by the EMF of this cell, and by measuring this EMF of this cell, so these following properties, the above properties could be calculated very easily. And not only that, the EMF could be determined very accurately by means of potentiometer, and so the properties we obtained from the measurement of this EMF of cells will also give this very accurate values. I shall already discussed several applications of this EMF measurements, but in this lecture I will give you a list of this of the applications and some new also applications I shall discuss. First applications I can say the determination of valency of the metal ion. Valency of the metal ion. Let us consider a cell and let us consider an electrode in flask of solution and this electrode. And this electrode, the reactions of this electrode is Mn plus Ne and gives this M, and this is in solution. This is solutions. So the potential of Mn plus oblique M give you the standard potential value of this Mn plus oblique M and plus at 25 degrees centigrade 0.059 by N and log activity of this Mn plus. Now suppose this solutions is 10 times diluted. Whenever the concentration of the solutions is 10 times diluted, the activity also approximately will be 10 times diluted. So in this case, say E dash Mn plus by M equal to E naught will remain the same as it is the standard value plus 0.059 by N and log approximately activity of Mn plus divided by 10. These electrode potentials are determined by coupling with standard or saturated calomel electrode, and the potential and this cell potentials are determined by means of this potentiometer. If we subtract this from this to this, means E m n plus oblique m minus E dash m n plus m, then this value will be this logarithm value will be log 10, and log 10 equal to 1, so this will be equal to 0.059 by n only. And so simple case, suppose one problem from this difference of these two values, this n could be calculated, and n will give you the valency of this metal ion. Very simple one problem I can set here. Suppose for the 10 times dilution of this electrolytic solution, this EMF changes by 0.0 electrode potential is changed by 0.03 volt. Then what will be the value of n? So from this we can get this n equal to 0.059 and divide by this value, this difference value daily. By changing this concentration of this metal ion by 10 times, this electrode potential is also changed by 0.03 volt. Let us consider. Then n equal to 2, as n will be the integer, so n will be given equal to 2. One historical important event is that the evaluations of this valency of mercury ion, and mercury ion could be determined by means of this concentration cell without transfer, and this is platinum, and I can write this mercury and this liquid, and here mercurous nitrate, say suppose C1 concentrations, C1 by 10 concentrations, and the solvent is 0.1 molar nitric acid, and it is the salt bridge is inserted. Right hand side, this mercurous nitrate of this concentration C1 in the same solvent 0.1 molar nitric acid, and here this mercury liquid, and this the platinum, and this one is the positive, and this one is the positive electrode or this cathode, and this one is the negative electrode of this anode. And we know this E cell without liquid junction is equal to 0.059, and divided by n. Suppose n is the valency of this mercury ion, and it is equal to log C1. This one will go upside, and this one C1 by 10. This one by 10. So this is equal to 0.059 by n, and from this n is found to be 2. So this was a doubt for so many years, and this concentration cell without a transference clears this event, and the mercury ion is written as this one and 2 plus. And now I may shift to this second applications 2, determination of activity coefficient of an electrolytic solution. Very important application. Electrolyte solutions. This is a very important applications of this EMF measurement, and by this way we can get this activity coefficient, and then the activity of this electrolytic solutions could also be calculated. So let us consider this cell zinc and zinc chloride. Zinc chloride solutions of this molality, say M. And right hand side is silver chloride, solid and silver. And this is positive electrode and this is the negative electrode. If we consider the cell reactions becomes Zn and Zn solid metal plus silver chloride, twice silver chloride. This is also solid, and giving this twice silver, and this is also solid, plus ZnCl2, and this is solutions. So Zn, if we consider this cell, EMF of the cell, then these three are solid and activity equal to 1, and this will give you this E naught shell and minus at 25 degrees centigrade 0.059 by 2 electrons are involved in this case, or 2 gram equivalent chemical change occurs, and this is this log activity of ZnCl2, and this E cell, E naught shell equal to E naught right hand side means chloride and silver chloride, solid and silver, minus left hand side electrode potential, standard electrode potential Zn2 plus and Zn. This one equal to 0.222 and minus this one minus 0.76 equal to 0.982 volt. So this one, and again the activity of a ZnCl2 for this electrolyte, it will be 4 and MQ and gamma plus minus Q, and this gamma plus minus is the mean activity, a coefficient of this electrolyte. M is the molality. So we can put here this is 0.982 and minus 0.059 by 2 and log this is 4 and MQ and gamma plus minus Q. And suppose, and from this if we determine this self EMF of this cell by means of potentiometer, then M is known from this electrolytic solutions, then gamma plus minus could be determined. I can set one example is that suppose E cell is equal to this E cell equal to 1.16 volt and M equal to 0.01. If we put here then it will be 1.16 equal to 0.982 and minus 0.059 by 2, and here log, and it is 4 into 0.01 and it is cube and gamma plus minus a cube. If we calculate this one, then gamma plus minus, this gamma plus minus will be equal to 0.699. Now I am coming to this third applications of this EMF measurement, and these values will give you the very accurate one. Now the third application, determination of the thermodynamical properties of the cell reactions. Already I have discussed this cell reactions is spontaneous, and the EMF of this cell is connected with these thermodynamical properties of these reactions occurring in this cell. And this first one, this del G at constant temperature pressure, and the process is reversible, and this one equal to minus NF and E cell, and this 2 del S equal to NF, and here del E cell divided by del T at a constant pressure, and this third one del H equal to NF, and here this T into del E cell by del T at constant pressure minus E cell. This formula already I have reduced, and this fourth one I can also put here. E cell not equal to RT by NF, and this ln this is equilibrium constant of these reactions, or at 25 degrees centigrade it is 0.059 by N, and this log equilibrium constant. So all these values we can determine from this could be calculated, this one calculated from this value of this, from the determination of this E cell by means of potentiometer. I can set one example here also. This is, let us consider this cell. Let us consider this cell is cadmium solid and cadmium chloride solutions. Here silver chloride solid, and this is silver, and this one is positive and this one is negative. So for this reactions, this N equal to 2. If we consider this cadmium plus twice silver chloride solid, and giving this twice silver plus cadmium chloride solutions. So N equal to 2. Suppose this E cell determined by means of potentiometer is found to be 0.6753 volt, and you know this E0 cell E naught cell equal to E naught of this right hand side, chloride ion and silver chloride solid, and silver minus E naught of this cadmium 2 plus and cadmium, and this one equal to 0.222 and this one is minus 0.40. So this is equal to 0.622 volt. And if we consider, then if we put here E cell, then equilibrium constant could be determined also, and every values could be determined. I can give these values so my dear students can calculate by yourself and find the result of whether this tally with this result I have given here. This delta G equal to minus 130.33 kilojoule mole inverse, and delta S equal to minus 125.4 joule mole inverse and Kelvin inverse, and this delta H is equal to minus 167.72 kilojoule mole inverse, and this equilibrium constant is very high and is found to be 1.2 into 10 to the power 21. So from this calculations we also see this reaction is spontaneous, delta G is negative, this is exothermic reactions, and equilibrium constant of this reaction is also very high, so the reaction is almost complete. Now I am coming to this fourth applications. Determination of pH of the acid solutions. I have already discussed several electrodes which are connected with this pH of these solutions, and the first one, this E and H plus oblique H2, this is equal to minus 0.059 pH. This is the first one, and first electrode which is connected with this is the electrode potential of this hydrogen electrode, and it is connected directly with this pH. And the second one, queen hydrogen electrode, E queen hydrogen electrode, and this is equal to 0.699. This is the E0 value of this queen hydrogen electrode, and minus 0.059 and pH. And this third one, which is probably the best one, the glass electrode, EJ, and equal to EJ naught asymmetric potentials, minus 0.059 pH. So by the use of the three sets of the electrode potentials, we can calculate the pH of this electrolytic solution. So let us take one example. Say here the saturated calomel electrode, here the salt bridge added, and HCl solutions whose pH HCl solutions whose pH is to be determined, and here the queen hydrogen electrode. This one is the positive electrode and this one is the negative electrode. So E cell which is determined by means of potentiometer is equal to this E queen hydrogen electrode minus E of this saturated calomel electrode, saturated calomel electrode. So this value is here 0.699 and minus 0.059 pH, and this value is 0.2415. If we do these calculations, then 5 from this to this, 5 7 and then 4 5, and this one is the 4 and minus 0.059 pH. If we could determine this E cell by means of potentiometer of this type of cell, this pH of this hydrochloric acid solutions could be calculated. And suppose E cell, I give one data, this one, say this one is found to be 0.3366. So putting this one 0.3366 equal to 0.4575 minus 0.059 and pH. And by this calculation, so we can get this pH equal to 2.05. Now the fifth one. Now this fifth one. Fifth applications, determinations of this solubility product. Determination of a solubility product of a sparingly soluble salt. Soluble salt. And one standard formula from the standard electrode potentials, already I have shown how this solubility product could be determined. Let us consider this sparingly soluble salt MXN and solid. This is the saturated solutions of this one. And this very relations, very good relations that we have already calculated. Here the standard value E naught and X minus, this may be the halogens, and X in solid, and here this metal, and this one equal to E naught and Mn plus and divided by and oblique M and standard value and minus RT by NF and this ln KSP solubility product of this salt MXN. These two are obtained from the standard electrode potential data table, and this one also at 25 degrees centigrade N plus oblique M minus 0.059 at 25 degrees centigrade N, and this one will be equal to log KSP of this salt XN. And I have already given this data or the how this could be solved. Now I am coming to the sixth. And the sixth one, determination of a transport number transport number of electrolytic solution. Let us consider the concentration cells. Concentration cells with the transference. Say it is the platinum, and here platinum, here this hydrogen gas, 1 atmosphere, and this HCl solution, and it is A1, and this one is cell membrane forming a junction, and here is the HCl and this A2 and H2 and gas, 1 atmosphere, and this platinum is a connecting metal, and this one is the positive and this one is the negative. So E cell with the junction, this one E cell with the junctions, already I have derived in my last class RT by F and ln A2 by A1, and this one is the transport number. Here this hydrogen ion. Now transport number of this chloride ion. Whenever this electrode is reversed with this cation, the transport number of the anion will come to these expressions of this cell potential. And whenever this one is taken truly without a junction, then it could be written as a platinum and hydrogen gas 1 atmosphere, the same cell, and here this HCl A1 activity, and here this silver chloride solid, and silver here, and here this silver chloride solid. Two cells are connected in series, and here this HCl and this is A2, and here this hydrogen gas 1 atmosphere and platinum. This one is positive and this one is negative. And already in my last class I have derived this E cell equal to RT by F ln A2 by A1. So from the ratio of these two, these are determined by means of potentiometer. So ratio of these two, we can get this T minus here this TCl minus chloride ions will give you the this is without junction. So this E cell with junction and divided by E cell without junction and gives this value of this chloride ion. And once the transport number of this chloride ion is obtained, transport number of this hydrogen ion will be equal to 1 minus TCl minus. Now I am coming to the seventh. Now I am coming to this seventh applications, and seventh applications is also important. Let us consider the weak acid and determination of dissociation constant. Dissociation constant Ka of a weak acid. And from this experiment we shall get this very accurate value of the dissociation constant of this weak acid. Let us consider this cell. Here this platinum and hydrogen gas 1 atmosphere, and here this weak acid H of this molality M1, and this is mixed with this sodium salt of this weak acid, and this is molality M2, and here another is sodium chloride, and this is M3, and here this is silver chloride solid, and this silver. Let us consider this type of shell, and it is the weak acid, and its potential, its dissociation constant is to be determined very accurately. So this cell reactions is cell reaction is the half hydrogen gas, 1 atmosphere, and this silver chloride solid, and giving this silver and solid plus H on solution and plus the chloride on solutions. This is the cell reactions. You could do by yourself, but H plus and Cl minus, we could not write here this HCl, as the H plus is coming from this weak acid and chloride ion is coming from this sodium chloride. These are the two different concentrations in this mixture. So this E cell potential, E cell equal to E cell naught minus RT by F. RT by F, 1 electron is involved, and here this ln activity of hydrogen ion into activity of this chloride ion, and rest are all unit activity. So this one we can write this one, the activity of this hydrogen ion, say this weak acid HA dissociates as H plus A minus. So the dissociation constant is activity of hydrogen ion into activity of this A minus divided by activity of undissociated HA. So activity of H plus, we can write this Ka into activity of HA divided by activity of this A minus. Inserting here, we shall get this one E cell naught and minus RT by F, and this is ln, and Ka into H, Ka into AHA into ACl minus, and divided by activity of this A minus, bracket close. This one equal to E cell naught and minus RT by F, and here ln Ka and minus RT by F, and ln activity of HA into activity of Cl minus divided by activity of A minus. So now you see the cell potential is determined by means of potentiometer, and this cell potential is connected with this dissociation constant of this weak acid. And now this one again I can write here this E cell, you can here gives this E naught cell, and equal to, and this activity of HA is the molality of HA and activity coefficient of this HA, and this one equal to 1, as it is the neutral molecules. Activity of this Cl minus equal to molality of this Cl minus into activity coefficient of this chloride ion, and activity of this A minus equal to molality of this A minus into activity coefficient of this A minus. Putting these values here, we can get this minus RT by F and ln Ka and minus RT by F into ln, and instead of this one MHA equal to M1 and this MCL minus equal to M3, and this is the M2 and minus RT and ln activity coefficient of this CL minus and the activity coefficient of this A minus. So again I can rearrange this one, this E shell minus E shell not here, actually E chloride and silver chloride is solid, and this is silver, and actually this value is 0.222 volt. I have already done the left hand side. The standard value is equal to this 0. So this one actually this E naught and silver chloride and silver chloride solid, and here this silver, and this one coming here plus RT by F and ln M1, M3 and by M2, which we have taken here concentrations and molarities, and this one equal to minus RT by F and ln and Ka and minus RT ln RT by F ln activity coefficient of this chloride and activity coefficient of this A minus. So whenever we vary, this one is determined by means of potentiometer, this one from the standard electrode potential table, and this, if we vary this one, then this will also vary, and this one remains a constant. This is the dissociation constant. Then if we plot, if we get a very accurate value, then this is the left hand side, and this left hand side is plotted along this y-axis, and the ionic strength is plotted along this x-axis, and this I equal to half a summation of mi zi square, and from these concentrations we can get this value of I. And whenever this left hand side is plotted by I, we are getting this plot which is a straight line, and usual the ionic strength is varied normally by keeping this M1 by M2 fixed, and only the M3 is changed. This is the usual practice. As M1 and M2, this is the weak acid and its salt, and these two are kept fixed, so that this according to this Henderson equation, pH will also remain fixed for these solutions. M3 is changed to have a different ionic strength of these solutions. Then this will be the graph, and whenever it is extrapolated, and this extrapolated value here, this ionic strength equal to 0, extrapolated value, And this, whenever the ionic strength is equal to 0, this one equal to 1, this one equal to 1, ln 1, 0. So this left hand side only gives this RT by F and this ln Ka. And at 25 degrees centigrade, we can write also 0.059, and this negative log of K means pKa. So this value, the dissociation constant of this weak acid, by this way we could determine very accurate value. And next, the last one, determination of this ionic product of water. Determination, this is 1.8, ionic product of water. And we consider similarly the same case, a cell is platinum and hydrogen gas at 1 atmosphere, and here the solutions is KOH and molality M1, and this KCl molality M2, and here this silver chloride solid and this silver solid, and this one is the positive electrode and this one is the negative electrode. And this cell reaction is again half H2 gas 1 atmosphere and plus the silver chloride solid, and giving you this silver, and this is also solid, plus H plus solution and plus the chloride ion, and it is also solutions. This is this cell reactions. And if we consider the potential, the cell potential equal to, it will be equal to A naught cell and minus 0 minus RT by F. 1 electron is involved in this 1 gram equivalent change, and this ln activity of this hydrogen ion and activity of this chloride ion here. In a similar way, this one could not be written as this HCl. H plus is coming from this KOH and Cl minus coming from this potassium chloride. Here this activity of this hydrogen ion and activity of this hydroxyl ion, and this one equal to Kw, and it is the ionic product of water, and this is to be determined. So instead of writing this H plus, we can write a Kw by activity of OH minus. Here putting this value, and this value in a similar fashion, it will be equal to E naught chloride ion and silver chloride solid, and this silver whose value is also known to us, minus RT by F and ln Kw into activity of this chloride ion and divided by activity of this hydroxyl ion, bracket close. And now you see how nicely this ionic product of water is connected with this cell EMF of these cells, and this one is the value we can determine by means of potentiometer. So E cell, next one, this one is E cell E naught chloride ion and silver chloride solid and silver, and this one RT by F and ln Kw minus RT by F and ln stick in a similar fashion, molality of this Cl minus and molality of this hydroxyl ion minus RT by F and this ln and activity coefficient of this chloride ion and divided by activity coefficient of this hydroxyl ion bus. Okay, and this one again by transferring this E cell cell minus E naught Cl minus. In a similar way, solid and silver, and this one coming here, so plus RT by F and Ln, and molality of chloride ion, molality of the chloride ion is coming from this potassium chloride, so it is M2 divided by M1, and in right hand side minus RT by F into Ln Kw, and minus RT by F and Ln activity coefficient of this chloride ion and activity coefficient of this hydroxyl ion. So again similar way we can, if we change this M1 and M2, this cell potential will also vary. So we can plot here similar plot, and ionic strength of these solutions will also vary whenever we shall change this M1 and M2. And so this will be the left hand side. Left hand side is plotted along this y-axis, and ionic strength is plotted along this x-axis, and similar plot is obtained, and this is the extrapolated value where I equal to 0. So this intercept value, when this I equal to 0, this value equal to 1, ln 1 equal to 0, so this value is coming here. So in extrapolated intercept equal to minus RT by F into ln Kw. And at 25 degrees centigrade it is 0.059 and pKw. And by this way, this pKw or this Kw, ionic product of water, could be determined very accurately by using this type of cell. And this is all about this eight applications of this EMF measurement. Each one will be very important in our calculations of the properties of the cell. And next lecture will contain specially the potentiometric titrations, and the potentiometric titrations will help us to have the various type of titrations, acid-base titrations, precipitation titrations, complexometric titrations, and the redox titrations, and so on. So let us thank to you all who are watching this video, and I hope if you like, then please subscribe. Thanks.